Double-sided flex, as I mentioned, 2 copper layers. The circuit here on the side is what's considered an adhesiveless layout. This material, the copper, is bonded directly to the polyimide without using an adhesive layer. There's a number of process techniques that suppliers will engage to do this. In some cases, it's a thin layer of polyimide material. Polyimide starts as a liquid and is cast out to a certain thickness depending on the film thickness that you're looking for. And in some cases, the polyimide film is not fully cured. So when the copper is laid against that material and put through the lamination process, the high temperature lamination of the polyimide will bond to the copper, providing that adhesive layer that bonds the copper to the film. On the right is your traditional adhesive bonded copper-clad film. You see that the material is a little bit thicker. So there are going to be some applications where the thinner material is going to be more effective or desired over the adhesive-based films. Multilayer flex is just the way it sounds. It's 3 or more copper layers. We stuck to 3 layers in this design just to keep it simple. But in this case, you see there's an adhesiveless polyimide layer in the bottom here, 2 layers of copper, a layer of adhesive, another layer of film. Like a PC board, these layers would be processed independently, individually, and then laminated together. I don't know how familiar you guys are with lamination processes or the actual PC board processes, but they're very similar, again, except for the handling. Then we have what's called a rigid flex. And a rigid flex is exactly what it sounds like. It's a combination of rigid materials and flexible materials built into the same circuit. This is a great example on the right here of a rigid flex where you need the flexibility between the rigid sections. And in this case, how many boards are there? 6 individual boards. Trying to connect those boards together with wires and connectors is very challenging. What we do is use we'll use a flexible layer in the middle of that stack up and bring that circuitry across what's called the flex area and bond it inside the rigid areas. For the most part, the thicker areas or the rigidized areas act just like a PC board, except you have that flex material in between. Now, there's some design techniques that you need to take into consideration when you're looking at a rigid flex, because there's going to be some other things we'll talk about in the coming slides. But in this case, there's a stack up here of the rigid section, which uses all your traditional rigid pre-preg materials, copper FR4s, and then the flex area that comes through. And one of the things we talked about already was this adhesiveless flex layer. And you notice that the cover layer doesn't go all the way across in the rigid region. Part of the problem with the flex material is that the adhesive layers are very soft, and the thermal glass transition temperature of the adhesives is much lower than the polyimide film and much lower than your pre-pregs or your FR4s. And when you've got adhesive in a stack like that, and you've got a plated through hole that has to go through an assembly process or any kind of heat or thermal excursion, the via holes can be jeopardized. So you want to be really careful in using adhesives through the stack up like that. That's why we replace the adhesive in the flexible and the rigid area with the pre-pregs. We're going to talk about optimizing designs. In this case, one of the things we want to consider is bending, and the circuitry, the geometry of the copper traces in the bend area can help or hinder your flexibility. In this case, you see on the right, the bend area is an area where the traces don't go across the bend area in a perpendicular fashion. That's going to cause trouble with your bending. It's going to force the flex to bend in a different way. The copper is a stronger material than the polyimide film, and copper is a metal, so it's going to want to hold the shape a little bit more, and it's going to follow the shape of the copper. So flexibility, bending, you want to be careful where you're designing the copper traces. On the left, the bend area, the flex traces go through the bend area in a perpendicular fashion, which is good. In the middle here, you see that the traces take a transition. There's different geometries here in the bend area. That can cause trouble with the bending. That could cause some high stress areas and actually cause the copper traces to break over time if there's too many bends that take place in that area. And you've got to consider handling. You've got to consider the final assembly. How is this circuit being used in the final assembly? And who's handling it? How do they have to handle it? So these are some of the things that you have to consider when you're looking at a flexible area. I-beaming is something that you probably never have to think about in a PC board design. When you've got copper traces that are stacked one on top of the other, it can cause compression and tension issues when you start to bend that flex. And you have a bend area across those traces that are one on top of the other. You want to stagger those, kind of distribute that stress across the bend area so that you have more flexibility and less stress and strain on the copper traces. Not to say that every design is going to fail if you I-beam it, but if you don't have to and you can get away with staggering those traces, you're better off. It's not something you really have to consider with boards because we're not flexing a PC board. A lot of questions come up when it comes to flexibility. There's calculations here. Basically, the bend radius of a flex is really geared around the elongation of the copper, the percent elongation of the copper, and how susceptible the copper is to breaking. There's a real good chart that came out of a book by Joe DiPalermo, who's been in the industry for a long time. And these general rules really apply. Single-sided flex, if you want to bend this flex, you want something that's 3 to 6 times the thickness, the overall thickness of the material. And this is going to help you prevent stress and strain on the traces or the film itself. Double-sided flex, because there's 2 layers of copper, because you may not be able to control the I-beaming 100%, you really want to go 6 to 10 times the thickness. And again, these are just general rules of thumb. Nothing's going to say that it will or won't fail at these numbers, but if you're looking at a design and you're wondering, how much do I need to bend or how much can I bend this, the minimum bend radius can be calculated in this way. Multilayer flex, again, depending on the number of layers, because it's thicker, there's more material in the bend, you want to tend to stay out to the 10 to 15 times the thickness. And again, these are just general rules of thumb. Dynamic flexing is continuous. It's continuous flexing. It's constant. There may be the same bend radius continuously for millions of cycles. And that's where you really want to be careful in choosing your materials. We're going to talk a little bit more about that in a little bit as well. But material choice plays a big role in that, but the bend radius plays a big role in that too. Back in the, I'm going to date myself here, late 90s, early 2000s when cell phones were developing and sliders and flip phones and all that stuff was happening, flexibility and electronics in the hinges, through the hinges, flex circuits played a big role in developing cell phone technology where it is today. Most of your phones today don't even flex, but you've got 5 or 6 flex circuits in there just because of the thickness, the 3D packaging, the lightweight nature of the flex versus the boards and rigid flex. So these are things to consider. If there's a ground plane, if you are 2 layers and you have a ground plane, you definitely want to be careful which side that ground plane goes on, whether it's in compression or tension in the circuitry. You just have to pay attention to what you're looking at and talk to your manufacturer. That's a big key. Find out what the limitations are, the materials you're choosing, and see what they recommend. Designing for strain relief. Flexible circuits aren't 100% flexible when you don't need them to be. We can add selective stiffeners. We can add FR4 rigidizers or polyimide extra layers of polyimide film. Any material that you add to the surface of the flex is going to affect the flexibility of that layer, that area of material. We selectively remove materials and add materials so we can dictate where the bend radius is going to start. If we add an FR4 stiffener onto a flex, depending on the bend area, depending on how hard or how harsh you're bending in that space, we might put a strain relief of maybe just a bead of epoxy across the interface of the flex to the rigid. That's going to help the rigid from separating from the flex and the high stress. And it depends on the application again. I can't stress that enough. Understanding how the flex is going to be handled at the end of the day, you're designing it or you're introducing it into a device. How is your factory going to assemble it? How are the people going to handle it? how's it get assembled in the final configuration, and what's the performance out in the field. You got to understand all of that when you're designing it, because now you need to know what materials you're choosing and how to design those layers properly. So the FR4 stiffener strain relief using a potting compound or an epoxy bead is very helpful. Tear resistance. Basically, there's been a lot of work done in the past where extra layers of material might be placed under the cover lay in a corner where we know that there's going to be a cut, and there might be these legs are going to bend up and be manhandled during the assembly process. We can add a little bit extra material on that corner. We could add a copper strain relief, add some blank copper that's in that corner so that if the flex does tear, it's got a tear stop and it can only go as far as the copper will allow it. That's just a preventative method. Understanding how your circuit design is going to handle, make a paper doll mock-up. That's basically what this picture is showing, is basically take a piece of paper and cut it into the shape that you're going to use. You'll see where the stresses are when you try to bend it and the paper tears. If the paper tears, you know you've got a stress point and you can design around that or work with it anyway. As I mentioned, adding copper around mounting holes can help. You got to be careful with mounting holes. People want to put screws through mounting holes, and you just got to be careful that the screw head is not going to come down and damage the copper. Some people want that copper exposed so that you come down with the screw and now you've got a ground connection, a mechanical ground to the chassis. So there are different things that you can do. You know, I'd highly suggest the stiffener, FR4, or just an added layer of polyimide material around those holes, just to make sure that it's strong enough and stiff enough to hold it when you do torque down that screw. And you got to be careful what the torque settings are going to be in the final assembly. Understanding the tolerances and understanding that, you know, flex material is flexible material. It's exactly what it is. When the material is manufactured, it's usually done in a roll form, and there are stresses that are built into that material as it's being laminated. The copper foil is being laminated to the films. And you might find that once the copper is now etched and relieved, that material can shrink a little bit, or that material can grow a little bit during the lamination process of a cover layer. So understanding your tolerances, if you've got a large flex circuit and you need something that's very tightly controlled from one end to the other, you have to be careful because there's only so much tolerance that we can build into a flex circuit, because it is a material that can shrink and grow depending on the processing. Ground planes are helpful. Power planes, ground planes. Added copper, as I said, can add stiffness to a circuit. But if you find that the copper is too stiff for your flexibility, you can crosshatch it. We go with a crosshatch technique that also helps in some impedance designs when you need that ground plane for reference to an impedance line. Crosshatching can have an effect on the impedance, sometimes in the good, sometimes in the bad. But working with the factory to understand what that is and understanding the flexibility you need for flexibility. This case, we also are showing a conductive ink. The ground plane or shield layer, if you will, EMI shield layer, could be similar to the polymer thick film that I talked about on slide one, that epoxy, conductive epoxy can be laid on the surface of a flex circuit and act as a shield layer. There's been a lot of development over the past 15 plus years in EMI shielding, which is yet another layer of flexible material that's bonded to the surface. Using conductive adhesives to make contact to an exposed ground trace, we can actually make that shield layer, tie it directly into the ground. So there's a lot of different techniques. I know I'm talking about a lot of different things here, and there's a lot to cover, and there's so many variables and variations that you can manage with flex. It's just understanding that what you can and can't do. But conductive inks, EMI shield films, crosshatch copper, these are all techniques that we can use to make a circuit more or less flexible as needed, or more or less functional as needed. So I mentioned earlier, copper being a metal will tend to hold the shape. You see in the bottom here where you've got some traces that go across the bend area. You just go straight across the bend area. If you find that this bend needs to hold a nice generous radius, but it's got to maintain a 45-degree around a corner type of thing. Enlarging those copper traces, making them a little bit wider where you can. The copper will overtake the properties of the polyimide film, and it's a metal. You can add the extra metal and hold the flex in its shape. So there are some design techniques that you can do there with copper, just to make things a little bit more flexible or less flexible as necessary. Choosing the right materials, designing flexible printed circuit boards. We want to make sure that the materials that you do choose are complementary to each other, not going to affect the outcome of your design or manufacturing. Understanding that when you choose materials, you want the factories to always make it the same way. So one of the most important things you want to do is capture your material stack or capture your material requirements on the drawing. Make sure that the factory understands that what you're qualifying or what you're testing has to be maintained over time, that you want it repeatable. You don't want anybody changing materials on you. So capture it on the drawing. It gives them, same with the PC board. You're going to define the materials on a PC board and probably a stack up. You're going to do the same thing with a flex. It's just there's going to be some additional flex specs that you might need to identify just to make sure that the factories are following your rules. Some of the things that we need to consider when we're designing the flex circuit: moisture absorption. Polyimide film does absorb some moisture. There's no doubt about it. When you design a flex circuit and you need to assemble a flex circuit, there's a good chance you're going to need to go through a baking process before it goes through final assembly. The flexible circuits are going through the same SMT processes as your boards. High temperature. Today's day, there's not a lot of people using low temp solder anymore. So those high temperatures are reaching 260 degrees C for up to a minute, and it's pretty high. So with the potential moisture absorption of the flexible materials, you want to make sure you drive that out by pre-baking before the assembly process. Flame retardancy. I had a great discussion with somebody here earlier today about UL. Some UL people here today. Understanding flame retardancy and the UL flame ratings on circuits, flex circuits, is important. Understanding that factories have specific stack-ups and specific material configurations that have been tested by UL and are approved. As long as you meet those same stack-up requirements, there's no changes. But if you need something special, they might need to test it. There's going to be a couple of months worth of testing and some cost involved in getting UL flammability ratings. But understanding the need, understanding that you know that you need to have flame ratings or not, or UL ratings. Make sure that your factories understand that, what you're looking for. Electrical properties, like any PC board, understanding the electrical properties of the films. Polyimide film is a very high-end material. There's some high-speed materials out there that are very specialized. You're going to be looking at higher costs, but factories do have them. So it's just a matter of understanding what your needs are, what you're looking for, and dictating or discussing that with the factories to make sure you know what you're looking for. Mechanical properties too. The first slide, the first couple of flexes are made out of polyester material. Polyester is very low cost material. It's a low temperature material, but it has its applications. If you don't need the high temperature applications of polyimide, you might be able to get away with a polyester film. There's also other films out there as well, PEN versus PET, different temperature ratings for different materials. So it's understanding that. Thermal properties are key. A lot of LED applications, the LEDs themselves, although they don't give off a lot of heat, the actual package itself, the LED itself, generates a lot of heat internally and needs to be dissipated. There's a lot has been done in the lighting industry with PC boards and metal clads. What do they call them? The metal core boards. Basically a circuit board with a layer of aluminum built into the middle of it to draw heat away from the LEDs. This has been done with flex as well. We've had some flex material that we actually had aluminum. The aluminum is bonded directly to the flex, and the aluminum draws the heat away just like it would in a metal core board. Now, the beauty of copper is a really good thermally conductive material. It's better than aluminum, but it's not as cheap as aluminum. So when you start adding aluminum, you start adding heat sinks to the back of a circuit, aluminum is going to be cheaper than adding copper. But if you're designing a flex circuit, you've already got copper in there, and you've got a layer of copper on the back side. We could tie that copper layer into the top side with via holes, thermal vias, if you will, if that's what they're going to be used for. But we could draw that heat away from a component by simply using the copper on the back side and positioning the via hole in the right spot to draw that heat away. So using the copper to your advantage and understanding what the thermal properties are. There are thermal adhesives out there that we can bond a flex to an aluminum heat sink if we choose to. And there are thermally conductive PSAs, pressure sensitive adhesives, that will take the heat from the flex circuit down into the into the aluminum carrier or aluminum heat sink. So these are the kinds of things to understand when you're starting off with the design. You mentioned some of the, I mentioned electrical properties of the films, understanding the dielectric constants, loss tangents. It's very much the same as what you're looking at in PCB materials, understanding, knowing what you're looking for from an electrical standpoint, and making that known to the factories. You want to make sure that they understand, or the people that you're working with understand what you're looking for, what the end result is, and what you're trying to achieve. Dimensional stability, understanding how the circuit is going to perform in its environment. What's happening? Where is this going? Is it an indoor-outdoor environment? Does it require 85% temperature humidity testing for outdoor applications? Is it an office product? Is it a handheld device in a warehouse? These are the things that you want to talk about and think about, and understanding the mechanical stresses of your circuit versus the electrical requirements as well. You know, a lot of people will save the flex circuit for last, and mechanical design is done, the boards are laid out, the mechanical chassis are done, the schematics are drawn up, but nobody thinks about the flex circuit till the last minute. We'll just make it fit. Well, sometimes it's better to start thinking about that in the beginning and understanding how you're going to interconnect the boards and how they're going to interface with the plastics or the chassis or the devices, and understanding the operator use and how they're going to manage the parts. You know, again, I said it earlier, and I say it every time I talk to a customer. I need to know what you're going to do with it. What are you going to do with my flex when I'm done? When I hand it to you, what are you going to do with it? How are you going to handle it? And how can I make it better for you? Everybody wants it low cost. I can't always make it low cost, but I can make it work. You know, and that's understanding the trade-off, understanding where you need to be and where you need to go with the design. Yeah, I mentioned consistency, lot-to-lot consistency, reliability, and making sure that the factory understands, or your fabricator understands your requirements, understands your needs. How is this device going to be tested later? You know, you've got to answer to other industries or other regulations. We just need to know what you're going to do for testing so that we can understand the material selection and help you guide you through that selection process. And I mentioned budget constraints, talking, you know, there are a lot of things we can do. Some will be cost effective, some will not be cost effective, but that's the trade-off you have to decide. Is it cost effective today or cost effective tomorrow when you try to put it together and you're able to? But if you use the wrong materials at the beginning and you have to remake it, now you've just cost even more money for something you could have avoided the first time. So it's flex circuit's not always cheap. It can be inexpensive. I don't want to say cheap, it's not the right word, but it's designing for manufacturing and designing and understanding what you're getting for the product that you're trying to develop. I mentioned some other different materials. PET material is very standard. This application on the left here is a combination of inside this plastic connector. This plastic connector is a molded connector that has a PC board inside with pins soldered to it. And then this FFC cable is actually soldered to the surface of the PC board. And then the PC board inside that shell is encapsulated. That's about a 10-foot long FFC cable that coils up on itself. It's a coil spring. Basically, it's a steering wheel application for a heater on an outdoor vehicle. So it has to unwind and wind as the steering wheel turns. So a clock spring type application. It's a fairly low temperature application, even though it's a heater for the steering wheel. The actual circuit itself doesn't get real hot. So it's a good application for that length of a circuit. 10 foot long PET circuit's going to be a lot less expensive than a polyimide circuit, and easier to build because it is a roll-to-roll process. The polyimide films, like I said, are very strong materials, high temperature range, really good tensile strength. It's interesting that the polyimide film is very difficult to tear unless there's a nick. If you nick it, it's going to tear like paper. But as long as there's a clean edge and a clean cut, then it'll be very strong material. So these are the factors when you're looking at a design: the mechanical outline of the flex. How's it going to be cut? What are the tools that are being used to cut? How are you going to handle it again during the assembly process? What's it going to come in contact with? How does it come across the edges of your chassis? Are you actually going to cut the flex when it's being installed? Is somebody going to accidentally drag it across the edge of a chassis that could actually cut the flex? So, I mean, flex is very strong, but again, it will tear if you get it to that point. PEN, I mentioned earlier, polyethylene naphthalate it's a little higher temperature than polyester. Again, it has similar higher tensile strengths, and they're all highly flexible. These materials are all highly flexible. Again, many of these do function in the hundreds of thousands and millions of cycles. And I think I mentioned the copper-clad laminate in some of the first slides with the actual, from a terminology standpoint, the copper-clad laminate is that FCCL, flexible copper-clad laminate, is what we purchase as a base material to start. There are different types of cladding. I mentioned the adhesive-based. You saw pictures of that. The adhesive-based materials versus the adhesiveless materials on the right there. High flexibility. The adhesiveless materials can get us those thinner constructions that we're looking for when we're looking for more flexibility. Thinness is usually a key factor in flexibility and being more flexible. Obviously, thinner is better. The adhesive-less materials versus the adhesive-based materials. Temperature range is something that we consider with the adhesive-less materials versus the adhesive-based. And again, adhesive-based materials have been used in the industry for years, since I want to say the early 60s when it was developed. Adhesive is typically an acrylic base, which is very soft, which is what makes it flexible. But over the past 15 years or so, epoxy-based flexible adhesives have also been introduced. There's a lot of acrylic epoxy blends that you'll find in some of the IPC specs. And it really depends on the material supplier as to what their capabilities are and what they have to offer and what you want to choose for your application. But flexible adhesives are as they say, they're flexible. And they come in a variety of thicknesses, anywhere from 0.5 mil to 2, 3, 4 mil, or 12.5 micron to 50 microns is pretty typical. The material suppliers, coverlay films come in ranges of 0.5, 1 mil, 2 mil, and variations, sometimes 20 micron instead of 25 micron, depending on the adhesive thicknesses and their flavors that they offer. So we can use all of these materials in very different ways when we want to get to a specific construction. So it's understanding what the suppliers can offer. Flexible circuits are used in many high-performance applications. You know, I touched on cell phones, but there's a lot more than just cell phones. Wearable technologies today are big. Body cameras, the phones, the watches, the Whoop watches, the iWatches. All of these devices, these smaller, tinier devices, are using smaller and smaller flex circuits. And again, they're assembled very similar to a PC board. The same processing, same assembly technique, just got to handle them a little differently and pay attention to how you handle them. Different types of copper. For a more flexible copper, the rolled annealed copper is usually the copper of choice. It comes that way. We buy it that way. It is a softer annealed process so that it is designed for flexibility. Electro deposited copper can be less expensive. It's not as flexible, but there are many, many applications, flex to install, or even low number of bend cycles. We can get away with electrodeposited copper. It's not a problem. Most of your boards, PC boards, are made with electrodeposited copper. So it's just the grain structure and how the copper is manufactured and how it's applied, and how it will perform in your bending. Now there are, I don't have a picture, unfortunately, of the high ductility ED copper, but that proved itself very helpful in some of the earlier cell phone applications with the flip phones and the slider phones, where you had about a 2 millimeter gap where the flex circuit had to basically roll back and forth on itself. And we found that even the rolled annealed copper was not performing as well as the high ductility ED copper. And part of that was the thickness, because the HDED copper could come in a thinner, much thinner form. We could get it in the 1/3 ounce, 1/2 ounce, 1/4 ounce, versus really 1 ounce or 1/2 ounce on the rolled annealed. I'm not even sure you can get 1/2 ounce rolled annealed. I think the lowest you can get is 1 ounce, but I may be talking out of school there. But anyway, so there are different types of copper, available that you can choose depending on the application. Stiffeners. I mentioned stiffeners earlier, Polyimide versus FR4, G10. FR4 is basically the flame retardant version of G10 material. Most of what we use in the industry for flex would be an FR4 type board stiffener. In this case, you see that the stiffener is selectively located. In this case, you see the black epoxy bead to give us a nice strain relief. You got this big, thick blade that's being mounted on a flex circuit, but it's got a backer board. It's got the FR4 for strain relief and support, so you can get away with that. But understanding the need, and the same board materials that you're designing, we can use as stiffeners. We just don't use the copper cladding. You design a board, you have a board that might be 10 or 20 or 32 thousandths thick. We can put as little as a 5 mil thick FR4 on a flex circuit, or we could go as high as 125. If it's out there, we can bond it to the flex. It's just a matter of what you need in your application, what you need in your installation, and how it's going to function for you. Metal stiffeners, I mentioned aluminum earlier as a heat sink. In many cases, stainless steel is being used against the back of a flex, where it's providing flatness that you might not get with a normal flex circuit. Again, it's flexible material. Once you start to laminate that material, there's going to be some waviness to it. The materials are going to take the contour of your copper traces. But if you need something that's flat, a stainless steel stiffener or an aluminum stiffener, other than an FR4, could be used. And the stainless steel could be used as part of the chassis. So it could be built right in where your flex becomes part of your chassis because it's on a stainless steel stiffener that gets built in. Plastic stiffeners are also an option, something that's pre-molded or over-molded after the fact. Typically, when you've got something like this, you're talking about tooling, you're talking about added cost for molding, but it's possible. It's not that it can't be done. Some plastics can simply be snapped on or glued or adhered with a pressure-sensitive adhesive, or you can go through a molding process. So there are different ways to use different stiffeners. The plastic stiffeners type would, obviously be something that you would design into your device. That's going to be part of the mechanical features of your device. So that's a possibility. I've touched on probably all of these different types of adhesives during the course of today. The acrylics are really good adhesives for flexibility. The modified epoxies have given us a little bit more stability than the acrylics. Those have been developed over the years. Prepregs, we use the same prepreg materials in a board that you're using in a board that we'll use in a flex. I've actually used a sheet of prepreg. It's very thin. A single sheet of prepreg might be 2 thousandths thick or less. And it's fairly flexible, even though it is a glass cloth and it is an epoxy adhesive. It's still very thin, and it's still fairly flexible. You just have to be careful of your bend radius and make sure that you're using the right bend radius. The epoxy glasses, the polyimide glasses, is your high temperature GI type materials. We can add those to a circuit as needed. I mentioned pressure-sensitive adhesives. A lot of flex circuits can be bonded into the chassis. We'll add a layer of pressure-sensitive adhesive to the back side of a flex or to the top side of a flex, and we'll cut it with the outline so that it follows the exact outline that you have. A lot of times we'll leave a little peel tab for you so you can pull off that release liner and stick it into the chassis. So these are all things that we can use to help fix the flex in the final configuration. Conductive adhesives, I mentioned that. There are electrically conductive adhesives. There are thermally conductive adhesives used in different ways. So they're out there. We have that ability to use them as needed, depending on your design and what you're looking for. And we talked about reliability, flexibility, and hopefully you're thinking about cost efficiency. You know, we'll work with you on material choices that are going to be the best for the application, but provide you with the cost structure that you're looking for. That's our goal. Picking the right materials that are going to work for you, but again, meeting your cost requirements. Now, that's key. It's always key. Using manufacturing practices, best practices. Using the proper tools to manufacture, the proper tools to assemble, and making sure that you're getting what you ask for and knowing what you're asking for. Flex circuits have been around for a while, and they're going to be around for a lot longer. Devices get smaller and smaller, flex circuits get smaller and smaller, and then all of a sudden things started to get bigger again. You know, devices get bigger, and as I mentioned, you know, earlier when flex became big in the phone industry, is because we had sliders and flip phones and all of that stuff. Now everybody's got a static phone that doesn't have any flexibility whatsoever, but there's still 5 or 6 flex circuits inside of there, primarily for space savings, for 3-dimensional packaging, and functionality.